Is it going?
Yeah, yeah.
Oh, cool. All right, so today, I titled my talk something about Hilbert Schmidt operators, but they're really only going to make an appearance at the very end because we have to do some work before I can even tell you why I'm interested in them. So let me start with, as promised, this theorem of Szemerezi. And I'm definitely missing some accents or something. But in 1975, he proved the following theorem. Let k be natural number. Let epsilon be greater than 0. Then there is some n and n. Actually, let me even make it stronger. There is some n0, so that for everything bigger than that, for all n greater than this n0, and any subset of the integers up to n, so long as I don't want all the subsets, just the ones that are big enough. How big is big enough? I want it to be at least epsilon proportion of n. And now what am I going to conclude about this set? S contains an arithmetic progression of,
Sorry about that.
length,
Thanks, you guys.
thank you, length greater than k, i.e., just to be really explicit about what I'm saying, i.e., there is some a and some d natural numbers, so that the collection a and a plus d and a plus 2d all the way up to a plus kd is a subset of S. So this is a really, this is a very strong theorem. Szemerezi proved this entirely combinatorially. He first proved what's called his regularity lemma, which in and of itself is a really useful thing about graphs. So just to indicate how strong this theorem is, let me point out the following corollary. Szemerezi's theorem immediately implies van der Waerden's theorem. So van der Waerden's theorem is, instead of fixing a density, I fix a number of colors, and I think about splitting this set up into a large but finite number of colors. And then I argue that some color class contains this arithmetic progression of length k. And how can you see that Szemerezi implies van der Waerden? Well, just let epsilon be 1 over the number of colors. When I color 1 through n, some color class has to have at least epsilon n many members. So then you get van der Waerden's theorem out of that. Let me talk about very briefly an equivalent way to formulate this, which is going to be sort of the way that I think about Szemerezi's theorem and how we're going to proceed, where instead of, like, we have this weird quantifier alternation right here, and we have to worry about exactly where this threshold capital N is, and with a few good definitions we can sort of simplify our lives. So, if definition, let's say that A, a subset of the integers, has positive upper Banach density. Oh, this chalk is very squeegee. Banach density. If there is, so when I write this down, it's going to look reasonable that this notion is going to be useful for thinking about Szemerezi's theorem. So A has positive upper Banach density if there is an epsilon greater than 0, so that for every positive natural number, there is some integer, so that if I look at the interval of integers m plus 1, m plus 2, all the way to m plus n, they intersected with A, I divide by n, and I demand that that's going to be at least epsilon. So the way to intuitively think about having positive upper Banach density is to say that I can find intervals somewhere where, restricted to that interval, A has a fixed positive proportion of membership inside that interval. But I don't necessarily know where that interval starts. This M gives me the freedom to shift that interval left or right as I choose. But what's nice is that this gives us the following. I'll write this as a corollary. Yeah, corollary of Szemerezi's. Actually no, I wanna actually say something that's formally stronger. Proposition. So sort of meta mathematically with this fact. Szemerezi is true if and only if every subset with positive upper Banach density contains arbitrarily long arithmetic progressions. And so this is a much more succinct way of thinking about it. We've got rid of this. We got rid of this quantifier alternation. We got rid of having to keep track of this primitive k. The only things we have to remember are we have a fixed positive density, and I mean, it's sort of cheating. There is quantifier alternation, but it's built into all these definitions. So does everyone? Yes.
Can you write down the definition of upper Banach density? Can you write down the definition of upper Banach density?
Oh, what that number is?
Yes.
It's going to be the lim. It's just going to be the lim inf over all such. It's going to be the lim sup of the lim. It's kind of annoying. It's the lim sup.
Epsilon that this holds.
Yeah, it's the best epsilon that you can do. Yeah, that's a good way of putting it. Thanks. But yeah, for our purposes, the exact epsilon isn't going to matter so much. All it cares that we can find some such thing. So this is all fine. This is just combinatorics so far. So let's see what happens 2 years later. So 2 years later, we have this theorem of Furstenberg. This was in 1977. Let x be mu t be a measure preserving system. I'll define what this means. measure preserving system, i.e. X is a set, B is a sigma algebra on X, mu is a probability measure on, I'll just say on B, and T is an invertible measurable and measured preserving, I'll just write mu preserving transformation. So given this data, what can I conclude? So let A be a measurable set with positive measure. Then, for every K in the naturals, there is L in the naturals with the measure of this rather large set, T to minus LA intersect T minus 2LA intersect all the way to T to the minus KLA positive. So this should look kind of reminiscent to what we have over here. Over here, we're looking for arithmetic progressions contained in a set of interest. Over here, we're looking for arithmetic progressions where a set of interest returns to itself. Superficially, it looks kind of similar. And it turns out we can do a lot better than superficially. So the first main goal of what I want to do is tell you in detail why this theorem of Furstenberg implies this theorem of Szemerezi. So, theorem. Furstenberg implies Szemerezi. Alright, so how might we prove it? So, I want to prove Szemerezi's theorem. So what I'm going to do is I'm going to let A subset of integers have, let me give myself a partition, have positive upper bound density. And let's unfold what this actually means. So let's fix an epsilon greater than 0 and intervals in of length n where we have the size of in intersect a divided by n is at least epsilon. So So I'm just hard coding in what my witnesses to having positive upper bonic density are. I would like to somehow, it seems kind of vague what to do at the moment. I mean, we need to cook up one of these systems and then argue that the recurrence over here gives us what we want over here. So, where do we start? Let's take the detour. Z acts on 2 to the z, just all the functions from z to 2. Equivalently, you can think of it as subsets of z just by what elements get 1. So z acts on this by shift. To be very explicit, I'm going to set t dot f of n is going to be equal to f of n plus 1. Another thing to be explicit.
Are you expecting pizza? Sorry.
I don't think so.
No? Okay.
Okay. Just to be, I'll take pizza, but say that f, we had in mind a set so that f was the characteristic function. So say that we had in mind f equals chi of s for some s subset. So then, I can tell you pretty explicitly that the function t dot chi of s, this is just going to be the characteristic function of s minus 1. Means I just take the set s, I just pull it to the left by 1, and that's a new set. That's what I get. So that's the end of our detour. How does that figure into this situation? Let's consider the following closed subspace of 2 to the z. I'm going to look at the closure into the z of t to the n dot chi of a, where n ranges over all the integers. So let's just observe x itself is z invariant because I just took a z invariant thing and closed it off topologically. I'm going to declare that this x is going to become this x. This is going to be the x that we're looking for. So we need all this other data. T is going to be straightforward. T is just going to be the restriction of this t to x. B is also easy. B is just going to be the Borel sigma algebra. But what about mu? Mu is going to be the weird one. I'm going to do some work to actually cook up the right mu. So, say, let's simplify our task a little. Let's start with a Clopin subset of x. Clopin. So what does that mean? Explicitly, B to me those f and x, so that f of k equals 0 for some k in a finite set f1, and f of k, maybe f0 makes more sense, f of k equals 1 for those k in some f1. So this is exactly what a Clopin subset of 2 to the z looks like, and I'm just restricting it to x. How am I going to tell mu? I need to tell mu how big b is.
What's F0 and F1 here?
They're just finite sets of naturals. Let me write that down explicitly though. So where f0, f1, subsets of integers are finite. So here's the idea. How often, let's keep track of this data. How often, quote unquote, does chi A return, let me get a partition here, return to B? So to make sense of this, let me cook up the set of return times. Set S of B just equal to those n, so that t to the n times chi of A is in B. Now we're sort of in a better situation, because now I have a set of integers, and I've also, remember at the very beginning, I sort of told you where A looked kind of large. I'm gonna take advantage of that as follows. So I'm going to, so if for people who don't like non-principal ultrafilters, just think weak star limit. We're just going to use weak star compactness and take a limit. But I'm gonna phrase it this way. So I'm going to let P and beta n be a non-principal ultrafilter. And I'm going to set measure of B equal to the limit as n approaches the ultrafilter P of this quantity. So intuitively, I'm saying, hey, these INs are the sets where A sort of looked big. So I'm going to look at the set of return times of A to B and sort of see how big these intervals think that SB is. And then since that limit might not exist necessarily, that's why we need to take an ultra limit and not just a limit. If you don't like ultrafilters, weak star compactness, that's really all that's going on. Yes?
Could you write down a definition of that ultra limit?
Oh, it's saying that I compute this number for every n.
Yeah.
And since it's between 0 and 1, there's actually a unique epsilon between 0 and 1, where for every neighborhood around epsilon, those indices where I'm very close to epsilon is p positive.
Okay.
So ultrafilters are nice. It's easy to check that so far we've only defined mu on the Clopins so far, but mu is finitely additive. On the Clopin subalgebra. Let me just say the Clopin algebra, that's clear. And so we have a finitely additive probability measure on a subalgebra which is dense in the whole algebra. So we can use, I want to say it's either like Carathéodory or Hopf, or someone has an extension theorem that lets you beef this up to a genuine probability measure. I'm going to call it Carathéodory. So,
Wait a second.
yeah.
Do you need like counter-additive to use Carathéodory?
All these Clopin sets are compact, so it is going to be countably additive on this subalgebra. Let's see. All right, so I've defined this measure, and now I need to argue that it does what we want, or why does the fact that I've cooked up this system do what we want? So let's consider the following properties. So as a warm-up, let's set B equal to those f and x, so that f of 0 equals 1. So I claim, what is the measure of B going to equal this weird ultralimit of the set cardinality I n intersect SB over n. But SB, let's just do this computation on the side. Anyone tell me for this particular B what SB is? It's those, what is SB? It's going to be those numbers, so that Tn of chi of A has the property. So what am I saying? I'll be explicit. This is equal to those n, so that Tn chi of A is in B. Well, to be in B, that means that at 0, I evaluate to 1. This is exactly saying those n. So remember how T had interacted with these characteristic functions. So that's just saying that chi of A minus n of 0 is equal to 1. And then this is just saying those n where chi A of n equals 1. And that's exactly A. So that's promising. We've got a system that really, it remembers something about A, and about how we code it in the fact that it has positive upper bound density. Oh, I guess I should have finished my sentence over here. One of the important takeaways is that since along these sequences we're always greater than epsilon, here we have a positive measure. So now let's use Furstenberg's recurrence theorem. Let's find some, oh, how did I phrase it? Let's find, so we should fix a k. Let's find an L so that the measure of t to the minus L b, actually I can even start, I don't have to start at t minus L, I can just start at b, measure b, intersect t to the minus L, b, intersect all the way up to t, so that minus k L b is greater than 0. This is what Furstenberg told us we could do. And now, what is this? Let's consider what is the set of return times to b intersect t to the minus L b intersect, so on. So I'm going to claim to do a little bit of calculation, but what does it end up being? It ends up being those n where, oh, I wrote it down pretty explicitly, those n, so that n and n plus L, all the way up to n plus KL, that whole thing is a subset of A. So if this receives positive measure, this set has to be non-empty. And that's exactly telling us that we found an arithmetic progression of length k. So it's a good start. So we've taken this relatively simple looking problem of arithmetic combinatorics and turned it into this rather frightening looking problem of ergodic theory. Progress. So I want to spend the rest of the talk actually giving you some of the ideas into Furstenberg's proof, like what are the main ingredients in that proof. I swear I'm gonna tell you what a Hilbert Schmidt operator is at some point. It's on the agenda. So I should tell you what a factor is first. So let x be u t be a measure algebra, or just be a measure preserving system. So given a measure preserving system, if I want to forget about null sets, I can. So it's very often handy to attach to these systems their measure algebras and kind of forget where you started and just think about measure algebra. A factor pi x to y. Here y is equal to some tuple y, let's say fancy d, nu, and another transformation t. So y is another measure preserving system. So a factor is a t preserving map t preserving, let me say mu preserving also. Let me call this mu. Mu preserving map from, so here's where it's a little bit weird, from the measure algebra of y to the measure algebra
those are actually two different measures, the same thing.
Yeah. So what the reason I do give them the same name is because the impression I want to give is that we have this measure algebra, and I've mapped it into this measure algebra, and the measure that we started with agrees with where you mapped it into.
Okay.
So to some extent, a factor map is just telling you a subalgebra of your measure algebra. So it is kind of an abusive notation, but it's not horrible to give this the same name. But the sort of the point to keep in mind is that for Furstenberg's recurrence theorem, we're really only worrying about sets of positive measure. So it's safe to, if you really want to, you can just do everything on the measure algebra level and not have to worry about points and such. Yes?
Did you explain exactly what measure algebra is?
Oh, it's just, so we started with our, say that B was our sigma algebra. And then I have this ideal, I mu is the sigma ideal of null sets. And so then I can just abstractly form, so malb x is just going to be B mod I mu. So I'm going to call two things equivalent if they differ on a mu null set. And then this in its own right becomes a sigma algebra.
Okay.
And the sigma algebra, like, you can attach a measure to everything in the sigma algebra. It's just a measure of a favorite representative. So alright, with this, so now that we kind of know what the factor is, what is the idea behind Furstenberg's proof? Well, Furstenberg realized, or I'm not sure if I should, how much credit I should give him for this observation, but he was definitely the first to take advantage of the fact that there are two sort of orthogonal types of factors that you can talk about. There are two really different ways in the factor map. So, idea behind Furstenberg proof. So, I'm going to start with one is going to be the trivial one-point system, and I'm going to start building. Oh, I should say, what am I building up to? Let's say that we're given a measure preserving system. So I'm going to start with the trivial flow. I'm going to call this x0, y0, x1, 1 to x2, x omega is the inverse limit of these systems. We keep going, x omega plus 1, pi omega, up and up and up and up. At some ordinal, we stop. That's alpha. But we might not be done yet. I mean, I haven't even told you what we're doing. So, and then there's going to be one last map. I'm going to call it pi alpha. And that is 1, 2 from x. So what Furstenberg proved is that there's a canonical way. What you should think about doing is I've taken X's measure algebra and I've built it up as a transfinite sequence of smaller measure algebras. Smaller but increasing measure algebras. Each of these in turn has a bigger measure algebra. So that the following things happen. What we want is that A the pi I for I less than alpha are what Furstenberg calls compact extensions. And the guy up top is what's called a weak mixing extension. So, proving this in and of itself is impressive. This is an impressive structure theory for measure preserving systems. Then, we have to argue that this recurrence property, and Furstenberg calls the recurrence property the SZ for Szemerezi, because that's what he had in mind. So argue that the SZ property lifts under both types of extensions. Under both compact and weak mixing extensions. So, just modulo the fact that I haven't told you what a compact extension or weak mixing extension is, that's kind of a roadmap for attacking the proof of Furstenberg's theorem. And with my remaining time, I want to shed a little bit of light on what happens at the very bottom of the tower, the very first thing that we do. So I will tell you what a compact system and a weak mixing system are. That's when they're an extension of just the trivial flow.
Just a question about the place where you terminate.
Here.
Yes. So, do you have to choose what alpha it is, or there's a natural point?
It's canonical. The way to think about the exhaustion is, so to x you associate L2 of x, and each of these are subspaces. Like the L2 of x0 is a subspace of L2 of x, and so you know that you have to stop eventually because you only have so many basis vectors in L2. So you have to stop at some point. And then you argue, but yeah, you're asking why is it canonical? You essentially, the way it works is when I'm designing this compact extension, I just pick the largest one I possibly can do at that stage.
The largest compact.
So I throw in, there are these compact functions that pop up. So like you get, once I hit x0, there are going to be functions compact over x0, and then I throw those in and I form x1. Then there are going to be functions compact over x1, and I throw those all in and I get x2. So that's very roughly. What is a compact function? I have to tell you. All right. Good news. Now I get to tell you what a Hilbert Schmidt operator is. So here's the definition. A Hilbert Schmidt operator I should really emphasize it. Let me, in fact, you can put an adjective, a concrete Hilbert Schmidt operator. H bar from L2 of x to L2 of x. So any operator of the form, so h bar of psi at the point x is going to look like the integral of h x x psi. I haven't told you what h without a bar is, but that'll be coming soon. For some h in L2 product. And I guess I should tell you what measure we're using. We're just using the cross mu on product. Alright, so I should convince you of a few things. First of all, why is it the case that if I take in an L2 function and I spit out this thing that I get an L2 function, we have to check some boundedness. But as you might imagine, Cauchy-Schwarz saves the day. So what is the norm of h bar psi to norm? And let's actually square it. So this is just equal to the integral of the integral h x prime psi of x prime d mu of x prime squared d mu x. And this looks very promising for using Cauchy-Schwarz. In fact, we can use Cauchy-Schwarz. So this is going to be on the outside. So we're just going to use Cauchy-Schwarz is going to happen entirely on the inside of this integral. So this is going to look like we have one thing of the form h x x prime squared d mu x prime. We have another thing that's the integral of psi x prime squared d mu x prime. This is all integrated over d mu x. Well, hey, this guy is a constant with regards to x, so I'm just going to pull that out. That's going to look like, that's going to be the square of that guy's 2 norm. And then suddenly what are we left with? We're left with double integral of squared d mu cross mu. Oh, and hey, that's just the square of h's 2 norm. So that tells us that at least I wasn't lying. This is an operator from L2 to L2. So what are we going to do? Why did I introduce these objects? Well, we're going to be interested in the case when this h I plug in is actually t invariant. Or it might be t invariant, it might not be t invariant. That's going to be an important distinction. So now, I can actually tell you a little bit about what these are. Not the extension bit, but I can at least tell you, because even the definition of a compact extension when your base system is non-trivial, it's kind of wacky. But when your base system is the one-point system, and you just have a compact system, the definition isn't horrible. So let's say that X is a measure-preserving system. I'm just going to suppress the B mu T, that's all understood. We say X is weak mixing. If and only if the product system, where I take the product segment algebra and the product measure and then just the transformation on each coordinate, is ergodic, i.e. the only T invariant functions h and L2 x cross x are constants. So weak mixing is a pretty intense property. And what we're going to do is, I want to end this talk by at least giving you the idea that we can get started on this tower. So I promised you that there was this string of compact extensions with a weak mixing extension on top. And so if my system is already weak mixing, well great, then we have this tower where alpha is just 0. If X is not weak mixing, then I had better be able to get started. I'd better be able to cook up an X1 that is a compact system. So what is a compact system? Once again, X is an MPS. We say X is compact if for every function in L2 we have that the collection of functions T and F, where n ranges over Z, is L2 norm precompact. This means that I look at this set of functions, I close it off under the L2 norm, and I actually get a compact subset of L2. And that's what are these functions? I'm just pushing forward the function. So the name of the game now is, if I have a system that is not weak mixing, I better be able to find a factor that is compact. That's what I'm going to try to prove in the next few minutes. So, and this is going to be a very rough sketch because it's where my notes start getting rushed in. So I may not finish in this last endeavor, but we will try. So here's a really important lemma. Say that H in 2x is not constant. This doesn't have to do with the fact that x is a system yet. This is just a general functional analysis. Set h prime of xy is going to equal h of yx. So I have these two functions, just one is swap the coordinates of the first one. Then there is a function in L2 of x. There is just some function so that either h bar of psi is not a constant, or h prime bar of psi is not a constant. And let's prove it. So, since h is not constant, I can find some sets A, B, C, D. Let me say that these are going to be measurable subsets of X with let's say positive measure mu positive. I'm going to say that A intersect C is empty, and what did I want to say? I want to say that the average integral h x y d cross mu divided by measure A times measure C. So the average of h over this rectangle is going to be different than the average of h over this other rectangle. I'll draw a little picture, because I think that will help. So we've got a situation that's kind of like this. So here's x, and here's x, and here's A, and here's C, and here's B and D going across, and here's A cross B, here's C cross D, and I'm looking at the average of H over this rectangle, and it's not going to be the same as the average over this rectangle. Arguing that you can get it with this disjointness is not too bad. If for every single pair of such rectangles they were the same, then you can just argue that h, the average of h was constant in every rectangle, so then h is just a constant, which is what we're not assuming. So now, let's focus on A cross D. So, the average, let's look at the average over A cross D. It can't simultaneously be equal to these two non-equal numbers. So without loss, let's say non-equal, without loss of generality, to, I'm gonna say that it's not equal to, is BC the one I wanna do? Let me, yes, CD is what I want. Wait, what? I drew my picture wrong. A, B, C, D. Yeah, okay, sorry about that. Okay, so without loss of generality, I'm going to say that that's not equal to this guy. Now, what function am I going to cook up? I need to cook up a function. I'm going to set psi equal to the characteristic function. And now, what's the convolution? So note, I want to argue that the convolution, since I set it up this way, I'm going to actually argue that this is going to be the one that's not constant. Note that the integral of h bar by du at a, and let's average by the measure, divide by the measure of a, this is going to be equal to this guy. I'm out of room to write, but this average is saying I convolve, yeah, so here's my characteristic function of D. And so I come across, and then I take the expectation this way, and that's going to tell, like I take the expectation of these fibers, that's going to tell me what this convolution is. So the integral here is nothing more than the integral of this little square. And then the integral, or I guess the, what am I trying to say? Yeah, that works. And then similarly, the integral over C h bar by mu divided by mu C. This is going to equal, and once again, I'm out of room to write, that's going to equal, oh, I got it a little bit backwards. This is going to be, this is going to be equal to this guy, this is going to be equal to this guy. These were assumed to be not equal. So then, that's exactly telling you that this function h bar psi is not a constant. That's good. So now I'm running out of time, but I'll tell you what the idea is. Or I'll at least tell you how we cook up x1. I won't be able to prove that it actually does the trick. But what you do is, in L2x, so let's look at, let's say that x v u t is not weakly extended. So this is the situation where if I want this tower to work, I had better find this x1. So consider the closure in L2 of the following set of functions: h bar of psi, where psi is an L2 of x, and h is gamma invariant. So since this system is not weak mixing, that means exactly that I have h's here that are not constants. Which means that I have functions here by this lemma that are not constants.
I guess I lost track. What's again?
T, sorry. So yeah, it turns out that this is going to be a subspace, this is going to be a closed subspace of L2. And then, if we look at, it's going to behave nicely with the lattice structure in a way that tells you what x1 is going to be. There's a criteria that Furstenberg proves for saying if you have, I have a Hilbert space of the form L2 of x, and I take a subspace and I want to know, is this subspace of the form L2 of y for a factor? There's a condition you can check that I'm forgetting, but you show that this satisfies that condition, and this is going to be, what you do is you set this equal to L2. This will be the L2 of this one. So sorry that was a little bit rushed at the end, but I hope that I at least gave you the idea of how the flow of this proof goes. The grimy details are kind of fun too. I would say if you want to read further, Furstenberg's book, Ergodic Theory and, is it just called Ergodic Theory? Is it like Ergodic Theory, Recurrence, and Combinatorial Number Theory? Yeah, so I'll just say book, Furstenberg. He published it in 1980. It's called Ergodic Theory. And some other stuff. But it's a really good book. Alright, I think that's it.
Any questions or comments?
So just to make sure I have the right theorem, the Szemerezi property is the measure of B intersect with.
Exactly.
So you can
So
have B in the.
yeah. So what's going on is we're looking at more and more and more of our measure algebra. So at the very beginning, you just have the whole thing. So obviously the one-point system has the Szemerezi property. And so then you're going to argue that I can throw more and more of my measure algebra into this collection of things that has the Szemerezi property until I've exhausted everything. The proofs, it's really remarkable because the proofs that it works for compact extensions, the proofs that works for weak mixing extensions are entirely different, but it works for each of them. Like they really are orthogonal situations. They have very little to do with one another. And Furstenberg was able to do both, which is impressive.
So I guess just to see that if you get to x1, it's just like one step closer to x is being closer to being this weak mixing extension of. So just trying to see just for this one step, is there any sort of barrier that we take away such that x is more likely to be the weak mixing extension of x1?
Well, we've thrown in, I wouldn't say barrier, but it allows us to make forward progress in that, so being a compact function, so remember, to be a compact system, every function in L2 had to be precompact. And being a precompact function is actually, that's pretty restrictive. Once we get to x1 and we're looking for x2, the criteria that we're looking for is a bit different. we're looking for those functions in L2 of x that are compact over x1. And being compact over x1 is going to be slightly easier than being compact over the trivial system. And so that's sort of what allows you to make forward progress. Okay.
Go back to the original theorem. So is there any growth condition on the n0?
Oh, like is it known the rate, like as a function of epsilon, how
That's
epsilon k,
yes.
Roy?
Something like tower, two.
Oh yeah, it's okay.
Of height, something like round that, so I don't know how it is.
No, yeah, you're right. And I think it was like, wasn't it quite a bit of work? Like at first the tower was height 1 over epsilon to the 5.
Yeah, and then they reduced it to epsilon squared, and then T always has a construction shows that at least the tower, the height of the tower has to be at least 1 less.
Okay, so it's
Yeah.
somewhere between, it's hideous, is the answer.
Alright, let's bear negative.